Okay. Hi, welcome to lecture 14 of Introductory Astronomy. So today we'll be looking at all different kinds of stars, single and binary, and for you to contemplate during the coming hour, or 15 minutes for people keeping actual time. Here is an interesting system. This is an illustration, and so you're trying to figure out what kind of system this is. What's going on in this strange star system? So this would be a binary system. But over to the obligatory slides so the people just tuning in know what's going on. This is Physics 1600, called Introductory Astronomy at Michigan Technological University. This is the 14th lecture in this series of, I'm not exactly sure how many. We're going up into the 20s. And I'm going to cover galaxies, the universe, life in the universe in the future weeks, so stay tuned. Today we'll be talking about stars, single and binary, and next time we'll be talking about star clusters. So I will be your professor, Robert Nemeraf, and if you want to take this for credit, then you need to go here, and you'll be asked for certain things. So as I keep saying, taking courses for credit costs money, but anyone can see these videos for free on the internet. So, if you are taking it for credit, you're responsible for the lecture material. As I say things, I will list Wikipedia entries every time. If there's higher math there, don't worry about it. I'm more interested in the concepts and the basic math. I'm not interested in the higher math. You don't have to reproduce the higher math. So every week I'll be reviewing the astronomy pictures of the day. And if you're taking the class, you need to take the homework quizzes, of which the first 6 are already due, as was the midterm, and 7, I believe, is due later today, and 8 will be released on Wednesday. So all the action happens at courses.mtu.edu. So today, you can review these on Wikipedia. This will be your textbook. Stars, Annie Jump Cannon, ooh, who's she? Stellar classification, binary star, and inverse square law will be the things that are discussed online in more detail than I will discuss here, but you're still responsible for things could be asked online. Don't worry, the quizzes, as you know, and tests are open web so that even if you miss things, you can go and look at them online later. Who is this woman? This woman is not Annie Jump Cannon. This woman is Henrietta Swan-Leavitt. And she helped, along with Annie Jump Cannon, who you'll see next slide. Okay, let's just show her. Calibrate the stars. So about a little more than 100 years ago, 110 years ago, Harvard College Observatory had lots of plates of stars, and they were hiring lots of human computers. Many of these, for reasons I'm not exactly sure, were women. And they looked at stars and they helped classify these stars. And these classifications, some of which were variable, some of which were according to types 1, 2, and 3, they were later moved to letters describing how bright the hydrogen lines were in different stars, became the basis for which we classify stars today, and for which we know, particularly the variable stars that Henry Swan-Leavitt calibrated, or had the idea they were the brighter ones were the further ones. This gives us a distance scale to the universe, which helps us understand the universe very well today. So even though they were paid a very minimal wage back then for seemingly minimal work, their contributions to astronomy were large. So this is Henrietta Swan-Leavitt, and this is Annie Jump Cannon at her work at Harvard College Observatory a little more than 100 years ago. So here's what they saw. They looked at lots of spectra of stars and plates of stars. And so here you see each line is a type of a star. And so the brighter stars, intrinsically brighter stars, are at the top. By intrinsically bright, I mean that if you put lots of stars all together, the ones that appear, if they're at the same distance, the ones that appear bright then, when they're all at the same distance, those are the intrinsically bright, the inherently bright. There are stars that can appear to be bright, apparently bright, that are not bright compared to other stars. They were put right up against those stars. For instance, our sun is apparently very bright. In fact, it's apparently the brightest star in the sky. But if you were to take it and put it next to Sirius, you wouldn't really notice it that much, because Sirius is much brighter. So even though Sirius is apparently dimmer, it is absolutely brighter. So here we see absolutely bright stars at the top, and you can see the bright stars tend to be the blue stars. So these, I believe, are the O stars, the brightest. Then come the B stars. A stars are next. F, G, K, and M. I'm not exactly sure which lines. Maybe the bottom line is only the M ones. So the letters originally meant how bright the hydrogen lines are, like these, I believe, are hydrogen lines. But later they were realized that certain letters corresponded to the blueness of the star, and we now know that that means the temperature of the star. So the O stars, we're going to find out, are the brightest ones and the bluest ones. The B stars are next. There are relatively few O stars around. Most stars are down near the bottom part. There's many of these, but the ones that you see at night, or the ones that you see in open clusters of stars, and the ones that delineate other galaxies, are typically the brighter stars. So this is at the beginning of what's sort of called the dark matter problem, although this isn't itself the dark matter problem. I'll describe that the brightest things you see are not necessarily cumulatively the most massive things you see. So even though an individual O star is more massive than an individual K stars, there's lots more K stars around than O stars. So as we know, our sun is a G star, which is about in the middle here. Okay, so two people did this independently. They created just a simple type plot to understand all the different stars on the sky. And this is, again, 100 years ago or so. One was Hertzsprung, and one was Russell. Russell, I think, working in the United States. They plotted the intrinsic brightness of the star, a luminosity, versus the color or temperature of the star here. I don't know if you can see that at the bottom. And they found that when you do that, stars don't just randomly appear at random luminosities and colors, that they bunch up in this diagram that's now called the HR, or Hertzsprung-Russell diagram. So this is an HR diagram. Hertzsprung-Russell diagram. So let's look at the different groups that formed here. Many of the stars form this band or sequence here. So that is called the main sequence stars. You'll almost never find a star here. So stars that have the intrinsic luminosity of our sun, they almost never have a blue color. You'll never find a star like that on the sky. So if you go over to here you find the sun fits in over there. Okay, so the main sequence stars are the most common type. Then another common type are giant stars. And another type after that are white dwarf stars down here. Again, when you get up into this area, these are 100 times brighter than the sun intrinsically and very blue. Down here, they are only a thousandth as bright as the sun and very red. Okay, here's a cartoon of the earlier picture. So this is luminosity in terms of luminosity of the sun. So again, here you see 1, putting our sun right there. Here you see temperature and spectral types. So again, the hotter, bluer spectral types are over on the left side, and the colder, redder spectral types are over on the right side. And here we see the main sequence again here. This line is the main sequence. Here you see red giants. Here supergiants are shown at the top, and white dwarf stars, which are actually very small. They're the end states of stars like the sun, are down there. So this has a better representation of where how many stars are where. Here you see most stars are down here at the dim end, and it's relatively rare to have a bright star, even though the bright star will outshine all the dim stars together. When we learn about stellar evolution, which we will not do too much this time, we will learn that many stars will evolve to become red giants, and some to become supergiants. The end states of stars like the sun and some lower mass stars end up as white dwarfs, which is, we'll explain that when we get there. So here are again the spectral types O, B, A, F, G, K, M. Now there are many mnemonics. There are ways to remembering how it is they go from left to right, from hot to cool, from bright to dim. Not all of them are politically correct. The most famous one, I will repeat for historic purposes, although it is not politically correct, it is. And I guess the G can change gender. It is O-B-A, fine, and it could be girl or guy, kiss me. That is the classic way of remembering this historically. Many times there are contests where people can come up with their own. I've seen some very funny ones, but none of them stick like that. The one I said is the most famous one. So don't sue me for repeating it. Okay, so here is again a breakdown of the Hertzsprung-Russell diagram in terms of where to find different kind of stars, which again is a bit of repetition, but the hot bright stars will be up here. They're hot because the temperatures are high over here and the brightnesses are high up here. The cool bright stars are over here. The hot dim stars are there. The cool dim stars are here. And the sun is somewhat close to the middle. So we live with an average star, a quite stable star in a very stable phase, which helps life develop, we think. Okay, so this is showing how large the stars are. This is in reverse order. So this is an O star, I believe, on the main sequence. This is a B star, and you can see, well, they're squashed up because I digitally compressed this image in the horizontal direction. So these stars are not oblong. Stars are pretty much spheres. But to get them all in one slide, I compressed this. So here you can see relative sizes. A is next. Here's the G star of our sun, and the M star we can see is really quite small compared to that. So we can look at this, but one of the great things about YouTube is that you get these really cool videos that are made by people who I'm not sure who they are. Some of them are wrong, but some of them are right and pretty cool. So we will now try to go to this YouTube address, and for some reason it won't click on it, so I have to get outside of, okay. So this takes about a minute. I'll start it up. So do you know how big the universe? Here is a minor view. So I don't know if I can make this the whole screen. Let's try. Yes. I don't actually had the music down before, so I don't know. So here you see planets. How big Jupiter is, Saturn is. Now here you see the planets compared to our sun. Our sun is much bigger than all the planets. Earth is shown there. Okay, now here you see our sun here is small compared to Sirius, Pollux, a bright star, and Arcturus, an even bigger, brighter star. And here you can see our sun is really small. Where is our sun? I can't even tell. Compared to, well, here's Arcturus again. And it's the largest known star is about 2,000 times bigger than our sun. Okay, so let's not watch the other ones. Let's go back. Let's allow us to do this. Okay. Okay, here's our sun. Arcturus. Let's follow the bouncing ball here. Here we go. Let's freeze this one. So I think one of these, our sun is here. It's very small. So you can see stars can get much, much bigger in our sun, and they can also get much brighter than our sun. Just because it's usually the bigger it is, the brighter it is, but not always. Okay, so let's try to get out of this. Minimize that. Go back to your program already in progress. Okay, now in terms of mass of the stars, again, you can plot these on a Hertzsprung-Russell diagram, and particularly for the main sequence of stars. Now, what is the main sequence? That's where most of the stars fall. It turns out the main sequence occurs when a star is fusing hydrogen to helium in its very center. That is a very stable process for a star to undergo. Stars have lots of hydrogen. And so the temperatures are hottest in the center, so they're always fusing that into helium. And that is a very stable energy source. For the most massive stars, it's a stable energy source for about 100 million years. And then it runs out and something extremely violent happens, usually a supernova. For the lower mass stars, it can go many billions of years. Our sun is 5 billion years old and still stably fusing hydrogen to helium as its primary energy source in its center. The lower mass stars are fusing at a lower rate, but they're still fusing hydrogen to helium, and they'll last for longer than 10 billion years. Here you see lots of low mass stars down here. They tend to be the K and M stars, and the high mass stars are the O and the B stars and the A stars up there. Okay, you can see stars at night have different colors. Although your night vision is not as good at seeing colors as your day vision, This is the belt of Orion, which is hard to tell. These are the stars in the belt of Orion that go 3 across here. And you can see they have some color. This is the nebula of Orion that you see has a slightly different, darker red color, but that's caused by an emission nebula phase, not caused by the color of a star. This is Betelgeuse up here. This fan is just a artistic blooming of the point image on this. I think it's actually, it wasn't done digitally originally. I think it is actually a photographic plate originally. You can see Betelgeuse is noticeably redder, more orange, than the relatively bluer stars of the rest that are bright in the constellation of Orion. So there are many famous stars. The Sun is probably the most famous star. It's so famous we just call it the Sun. Sometimes it's called Sol, which is sort of its name. The next most famous star is Polaris. There is a misconception that Polaris is like one of the brightest stars on the sky, but it's not. It's pretty bright. I think it's around second magnitude, but it's not one of the brightest stars in the sky. It's known because it is the North Star. So for us, it is always above the horizon. Even in the daytime when we can't see it, it's above the horizon. At night, when it's not cloudy, we can always look in some direction. So if you go out and stand in the same place and look relative to your house or dorm in the same place at night, and you're in the northern hemisphere, you should be able to see Polaris always pretty much right there. Doesn't matter if the sun just set. Doesn't matter if the sun's about to rise. Doesn't matter if you can't even see it because the sun's high up in the sky. Polaris is pretty much in the same direction all the time. The brightest star in the sky, however, is Sirius. It's near the constellation of Orion, but not in Orion. It is a very bright star, not all that far away. Betelgeuse is a big, bright star in the constellation of Orion. One of the reasons why Orion is one of the most recognized constellations. I find it usually by the unusual 3 stars in the belt that are pretty much the same brightness and pretty much in a line and pretty much the same distance from the center, the odd 2, the outermost 2. Known for its being near, you hear this a lot, but if you live in the northern hemisphere, you haven't seen it unless you've visited the southern hemisphere. That's Alpha Centauri, or the Alpha Centauri system. So we can't see it from here in the northern hemisphere. The Alpha Centauri system is actually at least 3 stars. Alpha Centauri A and B are the brighter, but the closest one is Proxima Centauri. It's in the out part of that system. I guess after a long period of time, it will no longer be the closest. But for the next, clearly 100 years or so, Proxima Centauri, which is not the brightest part of the Alpha Centauri system, is the closest star outside of our sun to us. One really interesting thing about the Alpha Centauri system is that I think it's Alpha Centauri A, not Proxima Centauri, is a G star, not very different from our sun. So it could be that one of the systems that shows life is not far away. In fact, it's in the closest system to our own. However, that system is at least somewhat different because there's Alpha Centauri B. It's got another bright star near it, and it's got another star, Proxima Centauri. So they would have a different sky. Things wouldn't get, as dark as things get during midnight and the new moon because most probably one of the other stars would be in the sky. Then there's Nemraf's star, which doesn't really exist, so I'm just kidding. Okay, so over to Polaris, the North Star. So you can find the North Star because the Big Dipper stars point to it. And I spent this morning trying to find the Big Dipper stars here again, and I've lost them. This, I believe, is the North Star. But these stars are streaks because the Earth turned during the exposure. If these 2 were the Big Dipper stars, they would point roughly to that. That's how I usually find it. I find the Big Dipper, and then I find the 2 stars at the edge of the Big Dipper that point to the North Star. This is unusual. This is a bright meteor that happened in the frame. Okay, so you can actually create time-lapse photography where the sky rotates. This one is a clickable one. I don't know why this one clicks and the other one doesn't. It's an astronomy picture of the day for January 10, 2001. And so let's see if we can refresh this and get it to re-go. So yeah, so I believe this is the North Star there. If you watch it closely, it doesn't move. The other stars, though, as the Earth rotates, appear to rotate around the North Star. So that is how the sky works and how you can locate the North Star. Trying to find the Big Dipper again. I think I might be wrong if this is the Big Dipper and this points to the North Star right there. Okay, so continuing on. Here's a time-lapse image, creating what's called star trails. So if you keep your eye can only integrate for about 1/10 of a second. And so you're seeing a movie in life where the frames are about 1/10 of a second long. That's the way your brain and eyes work. You can keep your eyes open indefinitely, but your brain will keep going and getting a new image from your eye every 1/10 of a second. However, with a camera, you can keep the shutter open and you can keep the image going for a long time. And then when we look at that, we can see star trails. So this is a star trail, and this is a star trail. The neat thing about the North Star is that it appears as a very little trail. So it is here. One thing you'll notice is that the North Star is not exactly at the North Celestial Point. So the North Star does actually do a tiny little loop around there. With the unaided eye, though, when you go out, it's going to be really hard to notice that. You need photographic equipment to notice the little circle the North Star is going to do around the North Celestial Pole. This is taken over Mauna Kea, Hawaii. Okay, so here's the South Celestial Pole. This is a really long exposure of 11 hours. So here you can see really long star trails that go over many times half the sky. Here you can see a meteor. You might notice that around the South Celestial Pole, there is no single bright star. So there is no South Star. The North Star is Polaris, but there's no South Star, at least right now. As the North Pole of the axis points in slightly different directions, it's going to move. So something like 10 to 12,000 years ago, the North Star used to be Vega. But then it moved and there was no North Star for a while, and now we're pointing quite near Polaris. The South Pole is not pointing right now near any star, so there is no South Pole star, so there is no bright star near there. This is just a weird picture where you can get almost both poles here. I think this is the South Celestial Pole here. The North Celestial Pole is right under this. So this is this image is squashed any number of ways. First of all, it's a long duration exposure. So this is a truly warped sky in many ways. So it is warped because the camera lens was kept open and the stars were allowed to make trails, at least when they were far from a celestial pole. It's warped because these star trails, this is a 180-degree image, so you could see all the way around, and the North Pole and the South Pole are visible in the same image. So here you can see these stars are circling the North-South Celestial Pole, these stars are circling the North Celestial Pole, and then you get this weird part in the middle where the stars are just tracking the celestial equator. And it's also digitally compressed to fit this screen, so it was compressed like this again. So all these warpings give you are taken of an actual real image of the sky and shows many different ways the North and South Celestial Poles almost on the same shot. Okay, I've shown you this image before. So this is a comet that was unusually bright, Comet Hale-Bopp. Here's the belt of Orion, as I've said. So here I believe is, okay, this is the belt of Orion. No, this is the Orion Nebula there. Let's see, this is the Pleiades star cluster, which will come up later. This is the belt of Orion I just pointed out. This is Betelgeuse, and I believe this is Sirius. So Betelgeuse, Sirius. So it's kind of fun to be able to go out and point these things. Around this time of year, which is late October 2008 when this is being recorded, you can see the constellation of Orion come up in the sky not too late. So you don't have to stay up very late to see it come up. And you can see these things for yourself, all but Comet Hale-Bopp, which is no longer there because comets come and go. Sirius itself is a very interesting star. Sirius is a binary star. So here is Sirius A, a bright, bright star, and there's a dim white dwarf star right next to it, Sirius B. There has been speculation, some weird speculation that have made specials about, I guess particularly on Fox these days, because they tend to go with the fantastic stuff, which isn't necessarily true. It's more important to be fantastic. It was thought by some for a while that Sirius B was mentioned by some old societies, some cultures. So when traveling to places in I think it was in Africa, they found an old tribe that didn't know almost anything about modern science. But what they appeared to know is that there was another dim star near Sirius. And people were worried, how could they possibly know that? And so it seems to be something, strange. How could it be something supernatural about their knowledge? Until you start to really look at the stories in detail, it turns out that there were explorers that had passed through that way before. And some of them had telescopes. And they most probably delighted in showing some things you can see with the telescope that you can't see with the unaided eye. And so they probably told them about Sirius B. And so when people came later, didn't know that there had been explorers passing by with telescopes 10, 20 years before. They were just amazed at these people's knowledge. But most probably this is just rediscovering a reflection of our own knowledge. Okay, Mira. We live in an age where we're actually able to resolve more than one star. For hundreds of years, more than that, we could see the surface of the sun. As long as you don't look at it directly, you can image it with a pinhole camera. It doesn't require any, all you need is a pinhole in a leaf or something, and then holding another leaf behind it. No sophisticated technology. You can see an image of the surface of our sun, and so you can tell there are things like sunspots. But to see the surface of another star requires a tremendous amount of magnification. And so, and light gathering power. So that has happened in these years. Particularly good at this is the Hubble Space Telescope. So here is the surface of another star that seems to show a big flare or something coming off it. And this is the star Mira. Now Mira is a very interesting star. Mira is a highly variable star and changes its brightness from not there in the sky, can't see it no matter how good your eyesight is, to pretty obvious, oh look, there it is. And that happens on the time scale of a year. So Mira is, there's other stars known like this now that are called Mira variables. You can go out and say, oh look at that star, and you and your friends can admire that star, and then you can go out several months later and nobody can find it. And then next year it'll be back again. We'll get into the science of pulsations later. But right now, just know there are some very variable stars in the sky. Our sun is very constant. Our sun would be boring in the sky of another culture. It wouldn't do anything like what Mira does. It would always be pretty much exactly the same. This star, HD12 Henry Draper catalog, the catalog number 12,545 in that catalog, so there's lots of stars that are known. You can see, if you're out in a dark location, you can see on the order of thousands of stars. If you're in the middle of a city, your average city, you can see, a dozen stars, dozens of stars. In the middle of the brightest cities, you can only see a few. So we're losing stars in our biggest city. And it used to be without, so city lights were only invented, 100 or so years ago. A couple hundred years ago, people were much more familiar with the sky and the stars than they are today. Today, we're more familiar with the science of the stars because we can go to the dark locations and look with more spectacular telescopes. And we can launch telescopes into orbit and see things in the most amazing ways. But the average person, besides seeing things on the web, doesn't see anywhere near as many stars as they have before. Here in Houghton, Michigan, we're pretty lucky. You can still go out and just go in a parking lot and pretty much see the band of the Milky Way and 1,000 stars or so. So I digressed, sorry. Here's the sun compared to HD 12545. The difference is the sun has relatively small sunspots as circled there, and I missed it. Let's try it again. Yes, got it. This star is thought to have giant star spots that take up most of its size. So again, we watch these stars for how bright they are. They change their brightness on the time scale of days many times, and this one changes the time scale on days, and we think the reason is that it has a relatively cool sunspot. on the order of 3,500 degrees Kelvin, as opposed to the other parts of the star, which go up to about 4,800 degrees Kelvin. Remember, our sun is about 5,800. So even though this is bigger than our sun, it is not as hot. Its surface temperature is not as hot. Due to its larger size, though, it's probably significantly brighter than the sun. Because you might remember, L goes as 4 pi r squared sigma t to the fourth. So temperature is roughly the same, but the radius of this HD star is much bigger. So the luminosity, the intrinsic absolute luminosity, is higher. But it will appear dimmer because it's further away. Here's another star we've been able to resolve, Betelgeuse. Betelgeuse. So here it's a little bit oblong here. It's circular, which just means that there's darker areas of this. Here's a simulation of Betelgeuse. Betelgeuse is thought to be a strangely variable star. Betelgeuse varies on the time scale of months to years in ways that we don't understand. We think there's unusual stellar activity on there, which could be these filament type things. They could be star spots. We're not exactly sure what, because we're only beginning to be able to resolve the star now. So this again shows us that some people think that science and astronomers have pretty much understand everything, and the purpose of this course is just tell you what we know. So we tell you what we know, you write it down, then you know everything there is to know. But that's just not true. Some of even the brighter stars in the sky have big mysteries that we don't understand. We don't know really why Betelgeuse is changing its brightness, on the time scale of months to years. So we're just guessing. So even you go out, you look at some of the brighter stars in the sky, don't know things about them. Still lots to discover about this strange universe of ours. Okay, so it is well known that here on the surface of the Earth that stars twinkle. So this is a video of a star twinkling. There's been several frames where there's these things called speckles, and these. So how do I explain this? The Earth's atmosphere is transparent, but it's a little bit like looking through frosted glass. Or they have these glasses, these plates in front of bathrooms that you can't see through. They're kind of fuzzy, and sometimes they're into little areas on them, and you can't really see through them. That is a little bit like what our atmosphere does. But our atmosphere does it because our atmosphere has regions of slightly higher density air and slightly higher temperature air. And so when you look in detail at that, then there's more than one light path that can come to your eye from any point in space, in particular any star. And so each of these light paths is shown as a speckle here. And these speckle makes these groups, and this group moves around. So these speckles move around. So if we go previous next, we can see this star pattern, and the speckles still tend to bunch, but they move around. Now, if you get something that is so large that it only moves around inside itself, it will not appear to twinkle. It is this moving about type thing that makes stars appear to twinkle due to our Earth's atmosphere. So the stars themselves are not doing the twinkling. Our Earth's atmosphere is making the stars twinkle because the average image of the star, first of all, the star is just a point, as best we can tell from the surface of the Earth. It's a point. It comes in as a speckle that's still too small for the eye to see. Groups of speckles are what the eye can sort of make out. But these groups of speckles move about on the time scale sometimes of seconds to make the star appear to twinkle. It seems to be moving around. But the star is right where it always is. It's the Earth's atmosphere that's slightly changing as it flows by us, as it changes in itself. The dense areas, the slightly warmer areas, are changing where they are relative to us and causes the light paths to change, so stars twinkle. If you have something really big, though, like a planet, of course a planet intrinsically is smaller than a star, but the face of a planet is bigger than the twinkling effect, usually. Therefore, planets will not appear to twinkle. And one way to tell a planet from a star is not only that it's brighter than most of the stars, usually the brighter planets, Venus, Jupiter, Mars, are going to be brighter than most stars. They're not going to appear to twinkle because the size of the planet as we see it on the sky is usually bigger than the twinkle pattern. Now, there can be times when the Earth's atmosphere is particularly turbulent, and there's lots of dense areas moving around, small dense areas, and lots of warm areas. And then you can even get planets to twinkle. And there are even times when after a rainstorm, when the Earth's atmosphere is very calm, and then it will be hard to detect the stars twinkling. But even so, for the most part, You can tell stars from planets because stars will appear to twinkle and planets usually will not. Okay, the inverse square law. So take a little divergence here, a digression, to show that remember I told you that L equals 4 pi sigma r squared t to the fourth. So this is intrinsic brightness, how bright the star really appears. So this tells us that big stars have intrinsic high brightness, and hot stars are intrinsically bright. But what would happen if you took something that was really bright and you moved it far away? It would not appear as bright. That's why L, which is apparent brightness, small l, goes like a constant over distance squared. Sometimes it's called r squared, where d and r are how far away. And this diagram shows why. So here you have all these lines where the photons are coming out of the star. And if you have a plate A that's going to catch some of those photons, if you put it near the star, you catch a lot of photons on your plate, a lot more photons than if you put it far away from the star. So you're not catching many photons. It's not appearing very bright as you move far away. And due to geometry, it's easily calculated as a 1 over r squared fall off. So here's another way to look at it, another graphic taken from Wikipedia. Here you can see all of these things, all of these points appear here. They appear here. They also appear here. But each of these individual squares, this is the same area, this is the same area as this, which has the same area of this. And you can see that the number of photons hitting that square has decreased. So it's, again, demonstrating the same thing. It's very simple if you think of it this way. Faintness means farness. Farness means faintness. Farness means faintness, usually. So this is something we know just from every day. If you see a dim street light, it's far away. You understand that. If you see a bright street light, it's most probably close. Okay, so here is a specific mathematical example. So let's say you have two stars, A and B, that are identical. They're not of A type and B type, as we discussed, but they're identical stars labeled A and B. So let's say we then take star B out to twice the distance of star A. The question is, how much brighter does star A appear than star B? That's the question. So you use the inverse square law that L, looks like an I, but it's an L, of the apparent luminosity of A drops as the distance to A squared, and K is just some constant. So let's look at it. L sub B is also equal to K over RB squared, just like this one was true for the A. Therefore, we can take the ratio of the two, and all we need to know, if they're identical, is how far they are away from each other, or compared to us. So here we have the luminosity A over luminosity B apparently is equal to, it would be K over RA squared times RB squared over K. That's the missing piece that then goes in there. So then the K's, which are constant, cancel, and you're left with RB squared over RA squared, the distance to B squared over distance to A squared. But we just said that the distance to B is twice the distance to A. So RB over A is equal to 2. And you put that in there, and then you square it, and square of 2 is 4. So the answer is that star A appears 4 times as bright as star B, even though they're completely identical. Here's a picture of Proxima Centauri. It's this guy right there. It is not one of the brighter stars in the sky, but since this is such a detailed image, it happens to be one of the brighter stars on this frame. Alpha Centauri is one of the brighter stars in the sky, but you can only see it from the southern hemisphere. So here it's fogging out this plate here. Very bright. Here's A and B shown in there. Here's Proxima Centauri shown there. I think Proxima Centauri might be visible down there too. Hard to see. Okay, on to most stars come in groups. It's unusual that our sun is all by itself. Our sun is just one star, the sun. Jupiter is not bright enough to be a star. Many stars, most stars we find are in different kinds of binary star systems. Now, a binary star system, binary means 2. That's clear. But the name has sort of been taken to mean multiple star system. So you can have a 3-star system and people still say, yeah, that's a binary star system. So there are certain types of, you can classify the different kinds of binary stars. One is a visual binary. That means that with your eye, and even with a telescope, you can resolve the stars into 2 separate stars. Another type is a spectroscopic binary. So it looks to the eye, and even through the telescope, as a single star. But as we'll see in a future slide, there appears to be a change in colors. And you can only get that change in colors by having 2 different stars of different colors orbiting each other. And then you can see, well, even if they're not of different colors, you can see when the star approaches you, you get a Doppler shift in some of the lines. Another type of binary star is an eclipsing binary. That's when one star moves in front of the next, just like the moon can eclipse the sun. However, usually the drop-off in brightness is not as dramatic as during a total solar eclipse. There's a slight drop-off. But if you keep looking, very carefully, night after night after night, you get these unusual dips where it becomes dimmer. The next type is an astrometric binary, where a single star will appear to wiggle slightly on the sky as it goes across. So stars don't move very much on the night sky, but they do move a little bit. So the fastest moving star is called Barnard's star. I think it moves like 10 arc seconds in a year. So you can watch it, over the time scale of a year, you can watch it shift slightly compared to much dimmer stars. Some stars, though, do a little wiggle as they go across. Why would a star wiggle instead of move in a straight line? Well, there must be another star there that it's doing an orbit around. So that star has shown itself to be part of a binary system, and it's called an astrometric binary. So I will now demonstrate these. This is Albireo. This is something you can get with a reasonable telescope, and this is a visual binary, because here we are resolving this into 2 stars. So Albireo, I think we've seen earlier in this course, is a bright yellow star and a bright blue star. And because the yellow star is brighter, we can infer that, and they're the same distance. They're not exactly at the same distance. But when you see a binary star or a globular cluster, the distances between the stars are so small compared to the distance between us and the star, we just say they're at the same distance. So that's what I mean. So Albireo, these 2 stars at the same distance, close enough. Here, the yellow star must be bigger than the bluer star because it appears brighter. And we know that from L equals 4 pi r squared sigma t to the 4th, if they're at the same distance, and we know that yellow is dimmer than blue, that for yellow to be brighter, it must have a bigger radius. So the yellow star must be a big, big star. Okay, so here we see 2 stars orbiting in a binary system. What they do is we say they orbit each other, which is true, but more accurately, one could say they orbit the center of mass, which is one of the foci of the ellipse that each of them go on. You can even merge these into a circle, and they could just both orbit in a circle around the center of mass, which is the center of the circle, which is the center of the ellipse, which is where both of the foci would lie. Okay, here you see the Big Dipper. Many of these are members of a single cluster of stars, and here, I think it's these guys you connect, and that points to the North Star there. Another thing is you can look at this star in the Big Dipper and notice that it is just on the verge of being a visual binary. In fact, some people can see it and some people cannot see it. So in some societies, when they're trying to find out who has good enough eyesight to be a warrior and who does not, they take them out and they say, look at the stars in the Big Dipper, which is part of the Big Bear constellation. Which of those stars can you see more than one star? And if they get the wrong one, then maybe their eyesight isn't so good. But if they get the right one, then maybe their eyesight is good, which is an indication with good eyesight that you might make a particularly good warrior. These stars are named Alcor and Mizar. So Mizar is the brightest one, and if you have a telescope, then you can actually resolve Mizar into more than one star itself. So that system here is actually a multiple star system. And the bright one, Mizar, is actually a binary. Okay, so this is a spectroscopic binary. This is an animation. got off from this address here on the web. You have to wait for it. So the observer is here. So you are here watching these two stars, A and B. A, let's say, has this spectral line here, and B is this spectral emission line here. As the two stars orbit each other, then you can see the spectral lines move with respect to each other. The Doppler shift will cause them, let's go previous next. The Doppler shift will cause the star moving toward you, that spectral line, to move to the blue end. And the star moving away from you, that spectral line will move to the red end. So I'll let them go through its paces once more, and you can watch as the stars go around relative to the observer how their spectral lines move. Okay, on to the next one. This is an eclipsing binary. There's two stars here. There's a big blue star and a relatively faint red star. So when the blue star moves in front of the red star, you get this dip. Time is in this direction in this plot. And so you get a dip in the light curve when the blue star moves in front of the red star. When the red star, smaller red star, moves in front of part of the blue star, you're blocking something that is intrinsically has brighter. Blue things have higher surface brightness typically than red things. So you're going to get a deeper dip. And if these two stars are not eclipsing each other, then we might not have known that they were in a part of a binary system. So this is an eclipsing binary. We see them because suddenly there's a lack of light that there was before. And eclipsing binaries can be very powerful because given other measures, we can actually measure things like the mass of the stars and even the radius of the stars. So eclipsing binaries are really great to find because they can help tell us a lot about stars in the universe. Here's another image of Mira. This time it's an artist's illustration which shows that Mira actually has part of its surface being brought off, circling another star in an accretion disk. So this is called an accretion disk. Right there. So this other star is pulling mass off of the brighter Mira star and going around there. This is why Mira might look strange. Here is part of the stuff being, we can actually image that as we saw before. You can find Mira yourself, but only when it's at its brightest, which you can find on the web when it's the brightest. So here is the Pleiades that we saw before, Aldebaran. The constellation of Cetus is here, and Mira, when it's visible, is down near the bottom of Cetus. So with this plot and the right time of year, and knowing when Mira is at its brightest, you can go out and see it. Okay, here you see a binary star system in the middle of a nebula that created this, this strange nebula here. They think it is the dim star. We think it's the dim star that has created this nebula. It's thrown off its outer envelopes. So when we do stellar evolution, we will talk more about how that can happen, how that star can throw out its outer envelopes and create very strange nebula like this one. Very recently, we found a binary system where there appeared to be a lot of dust. And we're not sure why there's lots of dust in this modern binary system. We think that possibly in this binary system, all this dust came from the collision of two Earth-type planets. Now, there is no planet that we know of that's on a collision course with Earth. Could it theoretically happen? Well, yeah. There could be something well out in the solar system, even that has the mass of the Earth. Or there could be something out in the galaxy that's just not very bright or hot. So it could be on a collision course with Earth, but we think that's very, very unlikely because we haven't seen anything zip by inside the orbit of the Earth that has the mass of the Earth or close to it. So we don't think anything like this is going to happen to us because most likely, it's like hitting the center of a bullseye to hit the Earth. Most likely you're going to hit the rest of the bullseye, which is the rest of the inner solar system. But here's an artist's illustration for two Earth-type planets colliding, and after they do that, they throw out lots of dust into the solar system, into that stellar system. So our knowledge of stellar systems continually changes. Back to the original image at the beginning of the lecture, this is called an intermediate polar system. And this is an artist's illustration again. This is also called a DQ Hercules type system. So here we have something called a white dwarf star, which we saw on the Hertzsprung-Russell diagram before. This is a big, giant star, I believe, and mass is being thrown off of this, taken off of this, orbiting here. But the magnetic field of this white dwarf star is holding out the material until it can't do it anymore, and until it's overloaded, and then it falls onto the surface of the star and creates a bright event. We will talk about novae, which these things might evolve into. So what you're seeing here is an artist's illustration of an unusual binary star system called an intermediate polar system. So we'll talk with lots of bigger systems next time, star systems, open clusters and globular clusters next time. And they do some of their own strange things, and they help us understand the universe in their own right. So we'll discuss that next time. See you then.